Edison, are those real piercings?
Nope. Jason, what are you doing?
Oh, look at that Minecraft though.
Minecraft looks amazing. All right.
My bad. I'm here.
All right. Let's see. Well, Blamio. Cool. So, shugs. Okay. So for the first bit of environmental on Monday, we went over so like the overall topic that we're going over is passive thermal systems. So for the first bit, we went over basic heating stuff. So like heat collection and heat distribution and whatnot. So now we're going to talk about cooling. All right, it's pretty cool. All right. Anyway, so there are many different ways of doing cooling. Okay. As a disclaimer, I have no idea what I'm doing. This is just what I could gather, so I may have some like inaccurate information, but you know what? It's important that we go over the slides. Van Lanningham didn't really go. I guess he sort of expected us to go over it by ourselves, so we might get some incorrect information. But you know, we're just gonna go over it. At least just go through the slides. So passive cooling design strategies. You know, there are many different ways to cool. There are many different ways to heat a building, and there are also many ways to cool a building passively without using any sort of mechanical, without using like any extra energy, like producing electricity for like HVAC or whatnot. So obviously shade, very simple, basic. This doesn't really cool down the space. It sort of reduces the amount of heat gain. A lot of the things that's in these slides are taking away heat, but shade, it sort of reduces the heat taken, so it's just less heat will build up. So external mass, cross ventilation, stack ventilation, night ventilation, types of ventilation, evaporative cooling, you know, whenever you sweat, sweat sort of appears on your skin and evaporates, it sort of cools you down. Cool towers, roof ponds, roof spray cooling, and earth tubes. I don't think there were any earth tubes in this presentation, but I assume it's some sort of geothermal cooling or something, because I don't know. Perhaps dirt is cool, and then you just put all the heat down there. So how well does it work? Literally have no idea what these graphs are trying to say. I assume UK uses a lot of energy, and then like all these things don't really use that as much energy. So you can see it's measured in kilowatts per square meter per fudge. I don't know what that is. Basically like use. I think that's over area. I'm not sure. But it's just like energy use. See these houses, they're using much less energy than like the entirety of a country, you know? Like obviously a country is going to be using more, but you average it out, and then you can see that some things can be much more efficient at using energy than other things. This is just a list of buildings with that use energy and that don't use energy because of like, I guess, climate and passive heating systems. So passive heating systems, they don't really use energy, which is a great thing about that. So anyway, cooling concepts. So cooling requires a large mass at a lower temperature than the space and people we are trying to cool. An environmental heat sink. Typical environmental heat sinks are air motion, ground temperature, bodies of water, the night sky. So in order to cool something, you need a separate entity, a separate body, in order to like accept the cooling energy. Right? So let's say you have, I'm gonna use Legos again. Let's say you have a bunch of heat inside this sort of structure right here. you want to cool it down, so you have to take the heat away. Well, where does it go? It goes to these environmental heat sinks: air motion, ground temperature, bodies of water, the night sky. You have to disperse the heat energy away from a building. So going over this again, cooling requires a large mass at a lower temperature than the space, so it can drive the heat away. Environmental heat sink. Okay, so this graph, I have no idea what this is. Barometric pressure, dry bulb temperature on the bottom. This website is out of date. Like it's not existent anymore. Dwellsol.com. So I'm not really sure what this means. Perhaps we are trying to achieve this design condition, this optimal temperature or something. And then you can see just like the natural trend of the different months, perhaps. I'm really not sure. There's this blue area that's not displayed, that's not labeled, so I assume it's just out of date. Hopefully Van Lettingham can go over this in detail on what this actually means.
This kind of looks like basically the
The
dry bulb,
psychometric chart, right?
yeah, psychometric chart. Like
Yeah,
if we
it's
overlay that, I think it's what it's trying to tell us is like what temperatures we should use for which, like which passive cooling methods for which temperature range. I think
Yeah.
that's what it's trying to say. And like that blue range is kind of like an optimal range for these colors, the yellow, orange, and purple, maybe.
yeah. All right.
Maybe.
Yeah. Santos, you taught me something.
Hey.
Yeah, so it does have. I'm pretty sure it does have like the exact same shape as a psychrometric chart. And just instead of relative humidity, it uses barometric pressure. For these diagonal lines or whatnot. Yeah, that's definitely, yeah. So if you're in this area, you would most naturally use natural ventilation. If you were down here, it would be better to use evaporative cooling. Yeah, very good observation. I like that.
And I'm more observant with Professor Edison than Professor Klebus.
Yeah, I like that. All right. Natural cooling versus natural heating. Natural heating works by converting solar energy into infrared heat even on a cool day. Environmental source of warm air is not needed. Natural heating, sun, equals or gets converted into heat. Simple stuff. Natural cooling systems run on different heat sinks and several different mechanisms to provide cooling relief. So this is why I said earlier, heating just comes from the sun, and then what blamio gets put on your building. Cooling, you have to take the already existing heat from your building and then drive it away using heat sinks. So, and remember what I said earlier about shade. It's not really a natural cooling system. It just reduces the amount of heat gain. So it's not real. So shade isn't really a heat sink. It's just natural heating lessened. Right. Any questions so far before I keep moving on? All right, coolio. Natural cooling versus mechanical. All right. So yeah, one thing about passive cooling systems is they don't provide humidity control because they cannot reach dew point in the warmer part of the years. So what is dew point? Dew point is just the temperature. So let's say you have a climate. What is the temperature at that current climate? That would make the temperature make the climate at maximum humidity, maximum relative humidity. So if you remember your psychrometric chart, where is my psychrometric chart? Somewhere here. I was not prepared. Hex yeah. There it is. Beautiful. So you have your camera, make sure. All right, you have your psychrometric chart with blamio. So you have a climate here. So you would just lower the temperature until it reaches 100% humidity, and then you know, then water would start to condensate from water vapor. Right. So I assume it's just extremely hard for to lower the temperature to that dew point, because it's lowering the temperature so much that passive cooling cannot really do that, and they don't really provide humidity control either. So that again doesn't help reaching that dew point. As systems do not provide reliable ventilation, air motion, and air filtration mandates of mechanical cooling systems. So air movement, ventilation for passive systems relies all on wind. It relies all on um, on the different atmospheric pressures to move air around, which creates wind. Because in mechanical systems, you can use a fan, you can use freaking HVAC or whatnot. But natural cooling, you rely solely on the wind. Right. Natural cooling. Defense first. What to do first when designing passive systems. Reducing internal heat gain. Lightly colored exterior surfaces, especially the roof. Vented skin structures, inadequate ventilation, shade windows. So this is just like basic guidelines on how to design passive systems. You're going to reduce internal heat gain. You're going to try reduce as much heat gain as you can. How do you do that? Shade. Light colored exterior surfaces so they absorb less heat again. Shaded walls, that I just said that. Shade, so the shade, radiant barriers and attic. So all this is trying to reduce all the heat gain first. Remember, defense first. You're trying to reduce as much heat gain before you start dispersing the heat that you already have. Right, so what's a good analogy? Let's say I have a glass. I have a cup, my Winnie the Pooh coffee mug, all right? And let's say water is heat energy. So you say you just pour a bunch of water in, right? And you get a lot of heat energy. You would have to pour that out, correct? But that's a lot to pour out. It takes quite some work. What you have to do first is reduce the amount of water being poured in, so then you have less to pour out. You have less energy. You need to use less energy to pour all that up. So defense first, reducing the amount of heat gain, right? Natural cooling components, interior heat from internal envelope gain, internal absorber, cool surfaces, thermal storage, the cool battery and mass, dissipator surface that dispels heat to environmental heat sink. So how does it work? So you have your interior heat from internal and envelope gain. So like just the heat that's already there and just comes into the building through internal absorbers, cool surface that absorb heat from interior, creates coolth by radiant or convective distribution. So just heat gain, essentially. Thermal storage, the coolth battery in mass. Dissipator, surface that dispels heat to environmental heat sink. Right, so you get all this heat, you store it up, and then you disperse it out. Questions so far? Just checking up. No? Beautiful. All right. Heat sinks, breezes, wind. Carry that stuff away. External mass, average day and night temperatures, including sunlit surfaces. So you just have like a big block of mass that would store the energy, and then through day and night cycle, it would help cool whatever. Help cool the building. Evaporation and evapotranspiration is just evaporation. Depends on the wet bulb temperature. So like if the wet bulb temperature is like the same as the dry bulb temperature, then you can't evaporate, correct? So it depends on the wet bulb temperature as well. Soil temperatures, thermal mass below grade, so you can just put that heat into the ground. I think that's how it works. Bodies of water, surface and groundwater. Water is really good at storing heat. So if you think about it, Right. So if you think about it, whenever you boil a pot of water, what becomes hot first? It's the pot itself, correct? Because it's metal, it's very conductive. So it's able to store, it's not able to store as much heat as the water itself. If you think about it, water takes a long time to heat up, so it needs a lot of energy. That just goes to show how much energy it can hold. So water is very good at containing thermal energy compared to metal, which heats up immediately, you know? And then the night sky. So, deep space is at minus 473 degrees Fahrenheit. I think this is inaccurate, so this is what came on the slide. I did some more research of myself, and absolute zero, the absolute coldest anything can get is minus 459.67 degrees Fahrenheit. So deep space is cooler than absolute zero. That just seems a bit off to me. So write this number down. I guess that's what Van Lanningham wants, but I'm not so sure about that. But anyway. So we're just gonna move on. This is just a repetition of the first slide I went over with all the different passive cooling strategies. But let's go over them again. Shade, external mass, ventilation, evaporation, water, and the earth. Basic stuff. Natural cooling versus mechanical. Wait. Didn't we already go over this? I do believe we did. Yeah, that's the exact same slide. Okay, cool. So ventilation, just like convection patterns. See, wind goes in here, will blamio, just like works its way around the room and just comes out. Passive cooling where's that one slide? Yeah, it's just based on wind passive cooling. So you just see here that here's just a bunch of different scenarios, I guess. I don't know where Van Lanningham got this, but just a bunch of different scenarios in buildings. You can just see sort of different wind flow and circulation, and more circulation inside a bigger room. So you can see the wind comes in here, and there's the exit right there. So yeah, like circulates right there. Will blamio. Right here, circulation. I don't think this is that necessary, but if you take a small interest in this, maybe you can like just stare at it and try to figure it out.
Actually, that comes in pretty handy for my current project for studio.
Ooh, then maybe you should take a screenshot, take a picture of this, save it on your phone, hang it up on your wall so you have easy reference. I think a good thing to have is to have a binder. So, and put like your psychrometric chart in there, put your shear and moment diagrams, maybe like ADA stuff, I don't know. Like have a binder for references that you like. So yeah, Santos, maybe you could put this in there. Yeah, you can probably get a clear image of it from Blackboard where Van Lanningham uploaded this. Alright, stack effect. Solar chimney. Buoyancy of warmer air creates a rising current that is exhausted as high as possible. So, back to third grade science. Warm air rises. So we want to capitalize on that. So the more warm air rises, the more cool air comes in. So make that warm air rise as high as possible. Take in as much cool air as possible, Exhausted air draws in cooler air from shaded areas of the site, producing air motion and ventilation even in total absence of wind. Heat rises, cool air comes in. The more the heat rises, more cool air comes in. Airflow can be enhanced by using solarization to heat upper end of the exhaust stack. So yeah, so at the top of the frickin' chimney, you can heat it up even more and make it rise faster, cool air can come in faster too. Solar chimneys. Stack effect ventilation can be used to create air movement and cool relief. Amount and velocity of air moved is proportional to the fourth power of the temperature difference between the bottom and top of the chimney. Why the fourth power? I have no idea. It's something to do with the Stefan Boltzmann law or Stefan's law. So yeah, if you're interested in why that fourth power comes along, you can look at that. If you can't tell, this was not part of the presentation. I just did extra research because I'm like, huh, why is that the fourth power? I still don't know. I was too lazy to read into all that sciencey stuff. Anyway, air motion is also accelerated by the height of the chimney. So, heat rises super high, and more heat rises faster, more cool air come in. Wablamio is just stacks on itself. Is he absorb solar energy at the top of the chimney? Oh, we just went over that right here. Works in any climate. That's always a plus. Right, so this Wymiana Sifla, that's actually in Polish for some reason. I had to translate that. It's just saying heat exchange. But yeah, that's in Polish for some reason. Anyway, so you can see the warm air come in, cools through the earth, and so you got a bunch of cool air, and then heat rises. So you see the sun on this chimney to heat up the air inside, which makes it rise faster, which pulls in cold air faster as well. I think it's the same thing here. You can see heat rise. Yeah, I assume it's the same thing here. There's a lot of words. You can see the arrow right here, indicating heat flow. Right, so Eastgate Office Mall Complex. Pretty interesting building. Very repetitive. Cool thing about this is it's got these freaking atriums, atriums, full of just like for natural heat ventilation. This is the chimney that we were talking about. Glazed atrium, low energy passive design features, direct and indirect solar gain minimized, night flush cooling of building mass. So get a bunch of heat in and heat out. Fun stuff. This is in Zimbabwe. Now we got to Zimbabwe. Let's go to Pakistan. See these freaking, I don't really know what these are called. Wind towers, that's what they're called. Usually the wind comes in, got some ventilation, and then, we got some warm air into here, cool air into here, and more exhaust. Wind in, wind out, heat in, and heat out. Fun stuff. I assume this is like very old technology because you see how old these photos are. It's probably made out of masonry. Like really old stuff. So
Pakistan's an old place, man.
Pakistan is an old place. I like that.
And all that right there, that's all load bearing. Bet you anything.
We all love our load bearing walls. All right. So, I think this is the last. Nope, not the last. We're getting there though. Night ventilation. All right. So, a cool way to. Cool way. I'm so funny. No, I'm not. Anyway, so a way to get rid of heat is through the ambient air temperature, right? Makes sense. Let's say you have like a burning ingot of metal or something. It's like at I don't know what temperature, like 800 degrees or something. And in order to cool that, it just uses the surrounding air temperature. Air temperature is like 50 degrees, 60 degrees, something around that ballpark. And then there's that 800 degree ingot bar, and it just dissipates the heat, right? We can do the same thing with buildings. So how do we get cold air? Well, easy answer is winter. But the even better answer is nighttime. You know, highs and lows. Nighttime much cooler because there's no sun. So, you know, ambient air temperature much better. So, ventilation of building internal mass with nighttime air. This is called night flush cooling. Is used to remove heat absorbed by the mass during the day and charge it with coolth to pre-cool the space for the following day. What does this mean? You have a building, it's got heat energy. Nighttime comes, takes away some of the heat energy. I think that's basically what it's trying to say. Right, so we have this Bates State Office Building, Sacramento, California. And this is also what this is saying. The Bateson Building case study. I assume this is kind of important-ish. Right, so you just see like the temperatures. If you just look over here, it's really hard to see with this resolution. Like you can see the different ways of heating and cooling. And just like different overall temperatures. So you see, well, heat balance. You see how it just fluctuates between the seasons. So we have the office building. Heat goes in through these south-facing movable louvers. Keep direct sun out of atrium in summer and let winter sun in for passive heating in the winter. So very smart. You know, you want to get as much heat during the winter. You want to get as least amount of heat during the summer. So make it open, get a lot of heat in during the winter. Make it closed and no heat for the summer. Coolio. And then cool night air is brought down the shaft, flashing heat from the atrium and rock bed. So it's just cooling. And there's like a bunch of different notes here as well. Skylight for year-round diffuse light, and just lots of cooling stuff. It's pretty cool. I hate myself. Anyway, moving on. Roof spray, evaporation, basic stuff. Evaporative spray roof cooling. Roof misting systems resemble irrigation system hardware. Will only spray a controlled amount of water for 5 to 10 seconds in order to flash cool the roof without overspray or runoff. So we're just covering the roof in a mist of water. They are controlled with greenhouse timers, and spray is overridden by a roof-mounted thermostat when solar air roof temperature are below thermodynamic wet bulb, typically between 90 and 95 degrees Fahrenheit. They work in all climates. Cover the roof in water, evaporate, we Gucci, you know? It's just like sweating.
Sweat.
Yeah, basically. You know, that's how sweat works. Or evaporating sweat. So yeah, just cover the building in water. And as we went over earlier, water can take a lot of heat energy. Water's pretty cool like that. So, and then it evaporates, it takes all that heat energy away into the climate, environment, atmosphere, fun stuff. Am I going too fast, or are we all good so far?
We're good.
You Gucci, my guy.
Beautiful. Moving on. All right. Evaporation. We went over this. Direct evaporative cooling adds moisture to indoor air to reduce dry bulb temperature. This can be as simple as a fountain or groups of indoor plants cooled by evapotranspiration. Man, combining these words. Why can't you just say movement through evaporation or movement through water vapor? Anyway. It also can be combined with stack effect cooling to create cool towers, which are not to be confused with HVAC cooling towers. Works in dry climates. Right, so instead of roof spray, which is spraying water on the exterior, I think this is adding evaporative effects on the interior, I think. So you have the fountain which sort of acts like this irrigation system that we went over. Or indoor plants, they can also evaporate, I guess, or like whenever you water them, you know. But, I think the difference between this is just this is on the interior. Let me actually read what this is. Indirect evaporative loss. Kind of important, I guess. Direct loss strategy. I didn't prepare for this. I don't know what that means. So we're just gonna move on. Next, yeah. What does ESRC stand for? Define ESRC. SRC. Oh gosh, that's a lot of economic and solar research. Maybe. Anyway, evaporative roof spray, ESRC. Maybe that just stands for evaporative spray roof cooling. Maybe, I don't know. Numbers, these are probably important. ESRC is an indirect loss system that reduces heat gain through the roof by evaporating a thin film of water, about 0.1 gallons per square feet per day. Right, okay, this starts to make sense. So roof spray doesn't take away heat that's already inside the building. It reduces the amount of heat gain from just solar radiation. So instead of solar radiation going into the building, going into the masonry, going into the wood, going into the brick, whatever, it instead goes into the water. And as we all know, water can hold high amounts of heat energy. So the heat gain gets transferred to the water. Heat flux off of roof is the equivalent of 8,800 or 8,800 BTUs per gallon. This eliminates 90% of roof heat gain. Okay, so this is a pretty cool cooling strategy. Extra benefit, longer life of a cooler roof that does not dry out or contract with daily temperatures or thermal shock of rain. So let's say you have a roof that is very resistant to water. Cover that roof in water and, eliminating 90% of roof heat gain. That's pretty cool. Ha! I hate myself. Okay. Evaporative spray roof. You see this freaking... See this mist? Mist. Covers the roof. Solar energy rather gets directed into the water instead of the actual building. And, cooling stuff happens from there. Night sky re-radiation. Night sky re-radiation cooling uses the roof as an indirect loss dissipator and the coolth of the upper atmosphere as the heat sink. So, just building, roof, building, that's like, I don't know, 80 degrees. Atmosphere, 60 degrees. Heat energy goes from high energy to low energy. Yeah. All right. Dissipation is enhanced by having highly emissive roof surface, but should be white to reflect sun during the day. Right? Makes sense. You should be able to dissipate as much heat as you can. That's what this means. Highly emissive roof surface. Have the roof be able to dissipate as much heat as it can. And should be white to reflect sun during the day, so reducing the amount of solar gain, so heat gain. Re-radiation to the sky is most practical in very dry, clear sky climates. Cool. Dry climate, probably easier to manage temperature without humidity, clear sky. Probably also has to do something with humidity. Cool stuff. Roof ponds. Okay, so this is actually kind of intuitive. So remember, water, it can hold a lot of heat gain stuff, Right, so roof ponds. Let's just go over this real quick. Night sky radiation control night sky radiation cooling systems use 3 to 6 inch deep roof ponds, opened or covered. We'll get into that later, or in a moment. As the thermal mass, the pond is protected by a movable insulation all day and exposed to sky at night. A metal roof deck acts as the thermal absorber from the interior. In winter, the pond is exposed by day and insulated at night, reversing the flow of heat and providing natural heating. What the heck does that mean? I found this image online. This was not part of the presentation, but I like a visual guide. So, water takes a lot of heat energy, you know? So, we have this roof pond that's exposed to the sun. Takes a lot of heat energy. Get as much of that stuff as possible. During the nighttime, it's winter, you know, so we need a lot of cooling. So we cover it to reduce the amount of, remember, night sky re-radiation, and have all the heat that's stored within the water, the roof pond, inside, right? Cool stuff. Now during the summer, opposite. You know, you don't want the water because it takes a lot of heat energy. So you want to cover that stuff during the day so it doesn't gain as much heat from the sun during the day. And then at night, you would open it to release all that heat energy that's coming from the inside of your building.
So you found this image on your own, right?
I found this image on my own. I needed a visual representation.
That's good. Can you like post it in the teams afterwards?
Oh yeah, totally. I will do that.
On its own, yeah.
Yeah. I just put that in the corner. Fun stuff. Night sky re-radiation. This is just using a small active system right here just to pump some. What is this? I assume it's some sort of water, some sort of medium to carry heat. And so you see how it's like warm air, and then as it goes through here, cool air, it becomes cool because of radiation to the night sky. Makes sense. We're getting there. Cooling system, earth tubes. Oh, we do go over earth tubes. Why didn't? Huh. Okay, cool. We do go over earth tubes. My bad. Earth tubes. Pre-cooling of air is achieved by contact between air duct tubes and soil temperatures at 6 feet or more below grade. Pipes are usually 8 to 12 inches in diameter to maximize earth contact heat exchange. Most of the cooling happens within the first 40 feet of pipe. Due to hidden condensation problems in the buried tubes, there are some health issues. So, this is a solution. Maybe not the best in some climates, but this is definitely a solution that you can consider. So, you know, you would have pipes 6 feet or more below grade, and the heat would just go into the earth. Fun stuff. Why earth tubes? This is what we need. Reducing heat pump size by 2 tons, 14%. That's a pretty big percent when you're talking about money, right? Like if you can save 14%, then why not? Saves 2,500 kilowatt hours per year, 10% of HVAC energy. Oof, that is another good chunk taken off of energy, you know? Good stuff. 40-year payback. Yeah, so after 40 years, it pays for itself, I guess. And 100-year life, don't know why that's question mark, but you know, if it has at least 99 years of life, or at least 40 years of life, then, you know, better in the long run. Cool. So, you know, 8 to 12-inch diameter for these earth tubes. You see how big those are? That's like, you see a human right there, that's the legs. You know, probably like, I don't know, that's big diameter. Yeah, you just bury that stuff in the ground. Heat just goes into the earth. Fun stuff. Underground earth shelter. Underground earth covered or bermed construction replaces the extreme variable temperatures surrounding buildings with the most moderate temperatures and thermal inertia of soil. The construction drawbacks have to do with waterproofing and water table levels, condensation, cold. Okay. So this is just going into a little bit more detail on why, or on just like conditions that earth pipes can work under. Right, so condensation, cold winter surfaces are a problem in some colder climates, so might not work as well there. It depends on waterproofing, depends on water table levels. So like, you know, moisture protection down there. Why am I all the way up here? Okay. Frank Lloyd Wright, the Jacobs House. Cool stuff. Okay, I think I was like too tired whenever I was going over these slides by myself, so I didn't even do any research on this, but write this down. It's probably important if Anlingham has a quiz on it. He might just ask you what buildings showed up in the presentation. So, you know, let's just go over those real quick.
Honestly, there's no telling what that guy would put on there.
But I would just like keep a mental note of these, write these down. Eastgate Office Small Complex in Harare, Zimbabwe. I don't know how to pronounce that. Got the Pakistan stuff right there. We got Sacramento, California, Bateson State Office Building. And we have Frank Lloyd Wright's Jacobs House 2. Combining systems, direct evap. Okay, I am. Okay, sharing. I, for some reason, just had this thought, like, wait, am I sharing?
Who knows,
Boy.
man? Who knows?
Maybe you're just looking at my beautiful face. It's not beautiful.
Hey,
Combining,
man, it's amazing.
direct evaporative, combined with solar. So, you know, just combining a bunch of systems, you know? Evaporation with solar chimney. Fun stuff. Solar chimney with earth tube. Fun stuff. Earth tube with shade and fountains. Fun stuff. Roof spray, roof pond. Fun stuff. Solar chimney aerodynamic form. Fun stuff. Building structure. Thermal mass for heating and cool storage. You can combine this stuff, you know? You don't have to go with one thing, you know? You can go for all of it. Extra cooling, you know? Use less energy.
Gonna be one cool building.
I've used that pun a lot. Alright, anyway. Hybrid systems that heat and cool. Roof pond with reverse seasonal operation. Remember the covering and the uncovering during winter and summer. Tromb wall, I don't know what that is. Give me a minute. Tromb wall, what is this? Images. Ah, okay. So it's sort of like a solar chimney. It like takes heat. It takes heat in, takes heat out, or it just takes heat in, heat out. Yeah. Internal mass for heat and cool storage. All right, so we've been using a lot cool. This word. PowerPoint's like, what does that mean? But it's just like, it's. Let me look it up again. Define cool. It's just like a way of saying cool energy, I guess. Pleasantly low temperature. The state or occasion of being cool. So you can have heat and lack of heat in traditional terms, right? It's either heat or lack of heat. Or you can just say in these environmental terms, heat and cool. Fun stuff. But cool is just essentially the absence of heat. Greenhouse, isolated again as part of a vented skin, earth sheltering in summer and winter. So these are just different things that can heat and cool at the same time. Well, not at the same time, but depending on what you need. Depends on the occasion. Is it summer? Is it winter? Is it night or day? Right. Enhancements. Evapotranspiration and shade from ground cover bushes and trees reduce the soil temperature for earth sheltering and earth tube cooling if irrigated. Cool. So ground cover, bushes, trees. Good stuff for earth tubes. Selective surface orbiters, not the radiant barrier type, enhances solar assisted stack effect and cooling tower applications. Right, so you can have different types of absorbent materials in a solar tower, or no, that's a cooling tower, you know, to add more heat to the top of the thing, at the top of the chimney to create a stronger convection or ventilation current. Nighttime roof spray with ponds aid cooling. Water. Oh gosh. Spray. Nighttime roof spray. Anyways, water and water. That's pretty cool. You know, the water helps the water because water plus water equals water. Water. Speaking of
Water
which,
squared.
water squared. Speaking of which, conclusions for natural cooling. All right, we are at the last bit of the slide. Reduce envelope heat gain first. All right, this is probably the most important part of the slide. If you were not paying attention, I completely understand, but if you were asleep, please wake up right now and look at this. Conclusions for natural cooling. Reduce heat envelope and internal heat gain first. Remember, defense first. You're trying to reduce as much heat gain as you can so you have less. So you can use less energy to take off the lesser amount of heat. Site plan to cool microclimate. Pay attention to your site, I guess. Vent the building skin and attic. Good stuff. Radiant barriers to help with heat gain or reducing. I think this is reducing heat gain. Yeah, radiant barriers reducing heat gain. Do not expect dehumidification. Right. So remember one of the slides earlier we talked about. Thing about natural cooling, it's not very good at controlling humidity. So do not expect dehumidification when you're using natural cooling. Use the sun to move air through system. So remember the cooling tower, we use the sun at the top of the cooling tower to drive all that cool air out. Fun stuff, you know? Just manipulate that sun. Shade, less heat, so it becomes cool, you know? Sun, where you want the exhaust, you know, or heat, heat rises, fun stuff. And combine and enhance systems and strategies. Don't have to go with one, you can go with multiple things. And if you do go with multiple things, you can also have them help each other. Symbiotic relationship, fun stuff. Any questions?
This is it.
Yeah. This is probably the most important slide. So, again, if you were asleep,
Why?
take notes.
Why is this the most important slide?
Because it's just a review of everything that we've gone over. All the core concepts, you know? I think it's the most important slide, but I could be wrong.
You know what else will save you 14% or more in your savings?
Bro, what?
You butchered that, Santos.
Man.
Also,
That's
this
a
was
shame.
probably the most disorganized PowerPoint I've ever been through in my life. Not on you, Edison, just on Van Landingham. Like, what kind of whack-ass fucking organization is this?
Yeah.
Right? Like, I feel like it's just so weird. There's random slides that are duplicated.
I guess just like
I
emphasis.
felt like a good amount of the PowerPoint was going over the same material.
And it was just really disorganized. I gotta hand it to Van Landingham for making learning as confusing and challenging as possible.
See, we got handed to Dale for being fast as possible. We got handed to Van Landingham for being confusing as possible. And we got handed to Klebis for being stressful as possible.
And I hand it to Edison for understanding it all. And helping us understand it.
Oh, thanks, guys. That really means a lot. All right. Any more? Oh gosh, I minimized that. Beautiful. All right. So, any more questions on environmental before we move on to my more Favorite part? Structural.
Man,
I'm gonna take a quick bathroom break, but I'll be back.
Oh yeah, let's take a break. Break time.
Quick bathroom break.
Minecraft break.
5-minute Minecraft break. Hex yeah.
Charish, you guys there?
Hmm. Alright, come back in at 8:40 or something. I don't know. 8:40 seems about right.
And we play Minecraft till 12 a.m.
I'm gonna grind some levels right now.
Not gonna lie, I might honestly just hop on World of Tanks.
Get a quick match done.
Yeah. The real game's 15 minutes long.
Oh,
Blitz
okay.
Blitz is 5 minutes long.
Okay, so you better play Blitz game because if you're playing World of Tanks during class, then I will kick you out and not allow you to attend my classes anymore. That's how professors do it, right?
Sounds like it.
Yeah. I love it. I am big sad. No one else is joining me.
Hey man, I'm already here. What are you talking about? Takes a second for my world to load up a little bit.
I'm gonna stop sharing. There we go. Alright. Dude, I remember, like, the last review session I had, we had like 19 people attend, which was amazing, by the way. Like, so many people joined, but this time I was like, huh, where is everyone? That's a shame.
Good question.
What's up?
No, I mean, like, where is everyone though?
Where is everyone? My feelings have been hurt.
Gotta put in the group me. You've hurt Professor Ed's feelings.
My feels have been hurt.
He needs a medic. He needs instant healing too after that.
Mm. Put in the chat, okay. Here, going over structural. No. Yeah. Maybe I'll incentivize some people to join.
Whoa, 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 whoa! What's this across the river? I see.
So,
Is that an enemy tank I see going after my oil rig?
this is a TNT cannon, chill.
Man has a cannon pointed at the Deepwater Horizon.
Don't press the button because it's actually loaded.
How are y'all's grades in tech? Are you guys doing okay?
I'm doing alright. I think I'm probably have an A.
Yeah, it's alright.
Not gonna lie, I don't even know. I don't even know.
Santos, turn your volume down. I can hear your music.
Sean, I know what you're talking about, man.
Oh, you're right. My bad.
That's Mars, my guy.
All right, fun stuff. 8:45. Shall we get back into reviews stuff?
Yes, because the server disconnected.
Rip. Okay. Oh yeah, it did. All right. So, what is up, everyone? Hope you had a very productive break. All right, we shall get back into the thick of it. All right, so we got my super professional whiteboard out. Very professional. Right.
Hey man, better than Clevis's.
Oh my gosh. I will not stop harping on him. All right, fun stuff. Okay, so structural. What the hell are we doing? Like, what are we doing in structural? We're learning about deflection. All right. So at the beginning of the semester, learn about moment, right? Moment. What blamio? We learn about shear, right? We learn about loads. Fun stuff. Moment is related to shear, and shears is related to loads, right? Now we're moving on to deflection. Right? So what's the difference between these two, right? Well, moment is a sort of thing that appears in all types of structures, right? So let's say, yeah, Lego. Let's say we have, all right, I'm gonna use green and red. Right, so, all right, let's say we have a green beam, right? Let's just say this is steel, and we have a red beam. Let's say this is, I don't know, wood. So if we put the same amount of load on each of them, I'm going to use a yellow brick. So if we put this amount of load on there, see how that yellow brick is in the middle of the green beam, and we have the same exact yellow brick, same exact load on the red beam, you see, they would have the same exact moment because it is a load and a distance, right? They would have the exact same moment. But what about deflection? How far does the beam actually move? I'm actually going to stop sharing real quick. Or, you know what? You can see my face. How far does this beam actually move, right? How far does the red beam move? How far does the green beam move? The green beam is hypothetically metal, so it would move less than the red beam, which we've stated to be wood. Now, why is that? It's because of the elastic modulus. It's because of inertia of those properties. So, moment. So we're just gonna make a little diagram right here. Moment. What is this? What does this take into consideration? Moment takes into consideration load and distance, right? Load and distance. Literally does not matter what the beam is made of. It's just a beam, you know? Now, deflection depends on moment. Well, I think it does. Anyway. Deflection probably depends on moment, but it also depends on E and I, right? So E, what is that? That's elastic modulus. Elastic modulus of the material, or another name for it, Young's modulus. Young's modulus. Same word for the same, different words for the same concept, I think. Fairly certain. 99.97% sure. And then we have I, which is the inertia. Cool. So, where do we get this? Where do we get this? Elastic modulus, inertia. Well, this depends on the material of what is this. So, you might have a beam, right, just like this. But in order to determine deflection, you need to know what material that is. What is this material? Wood has a different E value than steel. So this is what I was on about earlier. Green and red, they're different. Made of different materials, constructed differently. So they're going to have different amounts of deflection. Okay? And just deflection is how much, say, you have a beam. Gosh. Keyboard. All right, let's say you have a beam right here, You got a beam, you got a load. Deflection is just how much that moves, right? You have this beam, and then you put a load on it, and it becomes deformed, correct? Now, this was the original position. Deflection is just how long this is. How long this is. Deflection of a beam. You push it down, how much has it been? That's deflection. Right. So, gonna get into more, oh boy, more variables. Y'all ready for this? Hopefully. All right, so deflection. Back to deflection. Deflection, it's noted by a capital delta or a lowercase delta. I'm just gonna use lowercase. That's deflection. Okay. And this is gonna be measured in inches or feet. Doesn't matter. It's going to be measured in a distance, a unit of distance, right? So now we have stress. This is going to be measured. Okay, stress is noted by lowercase sigma, I believe. That's what that is. Stress, this is going to be notated in KSI. So a force over an area, right? So we can actually derive stress of an object. Sigma equals P over A. P being axial force. Remember internal forces that we learned? P was axial force, V was shear force, M was bending moment. So P is axial force and A is area. P being a force, so kips, pounds, and then A being an area, so like square inches, square feet. But for stress, we're just gonna a good unit that's reliable is KSI, kips per square inch. What's next? Elastic modulus. Let's go into elastic modulus. E. Or Young's modulus. I'm just going to do elastic modulus. Elastic modulus. This is going to be denoted in terms of KSI as well. Now you may be like, hold up. Stress is in KSI. Elastic modulus is also in KSI. What do we do? So, thing is stress is what's happening on the beam. Elastic modulus depends on how much the actual material can take. So stress, right here, it's under some stress. Wait, hold on. All right, scratch what I said. Right. So stress is based entirely on what's happening to the beam. Doesn't take into consideration what the beam is, just depends on what is happening to it. Pounds, or a force over an area. Do you see any indication of what sort of material that is? No. So elastic modulus takes into consideration what the maximum amount of stress an object can take. So elastic modulus, that is the limit amount of stress that an object can take, or a beam, or whatever. And this depends on the material. I'm gonna do a dot real quick, showing that this depends on the material. I'm gonna do a red dot for material and a blue dot for just what's happening on the beam. Okay. Material. And blue is gonna be beam. So does everyone understand what I'm trying to say about what's that like it's based on the material and like it depends on what's happening to it? Does everyone understand?
That's also for the inertia too, right? Like
Yes,
how
very
it's
much so.
Specific to the material.
Mm-hmm. Yes.
Okay, yeah, I'm getting that. Yeah.
Right. So elastic modulus is how much the material can take. Stress is just an umbrella term. Well, not really an umbrella term. It's just the general term describing stress, and elastic modulus takes stress into consideration. Right. So, what's next? Let's see. Yeah, let's go into inertia. Actually, yeah. Yeah, so right. Let's go into, we have three more things to go over. Three more units to go over, or variables. Right, okay, so strain. We're gonna go over strain. This is denoted by epsilon. Strain. Cool. Now what the frick is strain? This is gonna be measured in no unit. Question mark, why no unit? Well, let me just denote that in blue. So why no unit? Strain is just what sort of deformation comes from, just like the percentage deformation that results from stress, right? And deformation, I mean in deflection. So let me just write out the formula. Epsilon equals delta over length, right? Length of L is just length of the beam. L beam length. Right, so let's say you have a thing that's, let's say you have a beam, you have a wood beam, and its length is 360 inches. Is that, I forget how many, I can't divide by 12. 30 feet, right? 360 divided by 12. 30 feet, 30-foot beam, and its deflection is a whole 1 foot, so 12 inches. Actually, you know what? That's a little too much, but it's possible. But so let's say its deflection is 6 inches, correct? So length of the beam, L, that is 360 inches. You put a load on it, and it becomes deflected. This is still 360 degrees. Frig. 360 inches, but what it was originally, this deflection now 6 inches. So we're looking at this boy. We're looking at this boy. So 6 inches over 360 degrees, epsilon would be 1 over 60. 1 over 60, which is equal to 1 divided by 16, which is equal to 0.0167. So that's why it's unitless, because it's taking it's comparing how much it deflects based on how long the beam is. That's why it's unitless. That looks like an A.
So wait, just to double check, strain is deflection over length of the beam, right?
Strain is deflection over length, correct.
Deflection over length, okay.
So deflection is directly related to strain. Deflection, strain is determined by deflection and also length, but that's just going to be way too many terms on this one tiny page. Does everyone understand what strain is? Fun stuff. All right. Next thing, inertia. I, denoted by I, inertia. There's also different terms for this. You don't have to worry about this, but for those who are curious, inertia. So I went to engineering toolbox a lot while doing research for this. So yeah, so there are different ways of saying inertia, but inertia is just the general term that we're going to use in tech. There are also other technical terms, or more accurate terms. So they're called. So inertia can also be called, or should be called, area moment of inertia, or moment of inertia for an area, or second moment of area. You don't have to know any of that. We're just going to keep it simple. It's going to be inertia, and I'm going to denote this in red. You know what that means. It depends on what the material of the friggin' thing is. Let me just double check. Right. Hopefully. Okay. I'm not so sure about this actually, but okay, I am sure. So it's not derived from the material. It's actually derived from the shape. So maybe it is actually blue. Right? You know what? I'm gonna make another one. I'm gonna make a green one. Shape. So this is taking into consideration the cross section, right? So material, we have, oh gosh. So beam, we just have basic thing right there. Material is, what the frig is that made out of? And then shape is, well, what does that look like? Cool.
It's the I-beam, yeah?
Yeah. Or it could be a 2x4. Or a freaking 2x8. Or 2x16. Or 2x however. That looks weird. Anyway. So inertia is dependent on the shape. So what is inertia measured in? It's measured in inches to the fourth. Blamio. Why to the fourth? I don't know. You probably don't have to worry about it. But just know that's determined by inches to the fourth. And you know, one, so you can actually calculate the inertia for a rectangle. We went over this in class. Inertia of a rectangle is equal to b, or 1/12 times bh cubed. B being the width and h being the height of the rectangle. All right, fun stuff. And just so we're clear, let's say you have a beam that's laid vertically like this, right? So you're having load, it's like that. So if this is a section cut, take an elevation cut, it's like this, you know. Yay. Blamio. So H would be this boy, and B would be this one. So you see, H takes plays a much bigger role than compared to B. B still does play a role, but H takes the biggest role. Cubed. Have you seen the cubed graph? Let's look at that real quick. This is your regular B graph, right? That's like the higher B gets, the more important of a role it plays. This is your cubed graph. You see, so the higher your H is, it plays a much bigger role. Does that sort of make sense? So it all depends on the H. B does matter, but you can see H has a much more drastic effect on the inertia of a beam. Does that make sense? Does it not make sense?
Yeah, like the height is far more important than the base.
Yes. Yes. Yeah, we can also just look at it through trial and error. Let's flip it on its side. Section cut. Elevations. Elevation. So now this would be the H. This would be the B. See, now H is much smaller and B is much bigger. So B got bigger. It's not like it really changed that much, but H, oh man, that changed a lot. And you can also see this intuitively too. Let's say you have, I'm just going to use this Lego block right here. Yeah. Oh boy. Okay, cool. So right. I'm just gonna stop sharing so you can actually see my webcam. Right, so you have this Lego block, right? Height is more important role, right? So this is a section cut. Switch to elevation. I'm just rotating the view, nothing special. Put a load on this. Relatively easy because it's Lego, but all right, that was a bad example. I broke it way too fast. I did not expect that to break so fast. All right, anyway. All right, hopefully I'm weaker. So I put some load on it and it takes a while to break, right? But now what if I flip it on its side? Now this is the height and this is the width. Breaks super easily. So it's just a bit of intuitive critical thinking right there. So if you've ever went into your garage and found a 2x4 and stood on it, you would see that if you stood on it like this, it deflects much more than if you would stand on it like this. Much less stable. But if you have multiple of them in a row and a slab on top, it doesn't matter. It doesn't matter if they're vertical or not, because there's a slab on top of it, and it just takes away this small little area to stand upon. Right?
So this is just emphasizing the H in the inertia equation. Oh, got you. Okay.
Emphasizing the H. H plays a much bigger role than B. Right, so fun stuff. Section modulus. I think this is the last one. Right. Yeah. All right, so section modulus. I'm just gonna, we'll see. All this stuff. still length. Okay. Now we have section modulus. Section modulus. And that is, well, it's denoted by SX or S. I'm not really sure. I'm just going to use SX. Section modulus. Now this is determined by, or this is in units of inches cubed. Pretty cool. Now you can see that inertia is inches to the fourth. Section modulus is inches to the third. So relatively kind of similar, you know. It must be related, and you would be right. Section modulus. I'm not sure if this is for a rectangle or not, but this is just an equation I got. Section modulus is equal to the inertia beam divided by 1/2 of the height. Cool. So we can actually just drive this even further. What's I? Or I of a rectangle. So we can find the section modulus of a rectangle real quick. I is 1/12
BH cubed.
BH cubed divided by 1/2 H. Oh, I erased that formula. I'm gonna rewrite that. Add that back in. So H's cancel out, or H's, this cancels out to 2, and this cancels out to 1/6. So section modulus of a rectangle is equal to, let me just make sure I'm doing this right, 12, 2, right, okay. Section modulus of a rectangle would be equal to 1/6 of b times h cubed, squared. So you can see b h squared, that's an inch unit, that's an inch squared unit. Multiply them together, you get an inch cubed. Bam, this would, fun stuff. B h cubed, inch cubed, cubed. Multiply that together, inch to the fourth. Fun stuff. I'm just gonna go back. So inertia of a rectangle is equal to 1/12. Gosh, why did I write 1/12 b times h cubed, right? Section modulus of something is the inertia divided by 1/2, 0.5, 1/2 of the height. Fun stuff. So let's say you have an I-beam. That's a terrible I-beam. Well, let's just say you have inertia. You just divide it by this length to get your section modulus. You know that this is h. Or actually, I should do this with just a regular rectangle, right? So this is your h right here. It's going to be your natural axis, or is it natural or neutral?
Neutral.
Neutral, okay. All right, so neutral axis. So this is your neutral axis. And so this is your height. This is your height divided by 2. So you're just going to divide I by this, divided by this one right here to get your section modulus. Fun stuff. All right. All right. So boy. So now, let's say you don't have a rectangle let's say you don't have a rectangle and you want to find the inertia value, right? Because I've only given you the inertia, the inertia equation for a rectangle. What if you don't have a rectangle? What if you have an I-beam? Well, there's actually an equation for that. Problem is, it's just going to be more rectangles, but we're in the basic area, so it shouldn't be a problem. There's not going to be any like triangles or anything, and like beams probably aren't even made from triangles. They're probably made from rectangles. So I of rectangles, rex, you know? What do I mean by this? So you have an I-beam. Ah, that's a T. I-beam. Sorry, wide flange beam. Aha, gotcha, Clevis. All right. So you see, if we divide it into little sections, you see there's a rectangle here, there's a rectangle here, there's a rectangle here. Fun stuff. But you can also like divide like this. It'll be like 5 rectangles. 1, 2, 3, 4, 5. Or you could do it like this, where it'd be 4 rectangles. 1, 2, 3, 4. You can divide up essentially any shape you're given into rectangles. Easiest way for a wide flange beam is to divide up like this. 1, 2, 3, easy stuff. So inertia of rectangles is the summation of the inertia of a rectangle. Right? I'm not going to do it that way. 1 over 12 times BH cubed. Actually, you know what? I will write it that way. BH cubed over 12. Basic algebra. See, I just moved this term or this group of numbers on top to the numerator, and it just doesn't change the formula. It's just a different way of writing this. BH cubed over 12 plus AD squared. D is the distance that whatever rectangle you're using, the distance of that, the centroid, the distance between the centroid of the rectangle and the neutral axis. What does that mean? Wide flange beam. It looks so beautiful. I'm going to divide up into more rectangles. You have this boy right here, right? Now, the H might not be so big, and remember we did emphasize how big of a role H played. But we have this D squared right here. So D squared takes well, because this is inches squared, this is also inches squared. Perhaps they play the same role, same amount of role. But anyway, we have the centroid right here. So that's natural axis. This coming across. Centroid right there. Right there. That's the center of the rectangle. We have the neutral axis right here. So that's just this distance right there. And that's just what D is. So if you make it farther away, you know, it'll play a much bigger role. So just graph that real quick. So let's say you have this graph, right? Let's just say D was 1. Let's say D didn't play that much of a role, right? 1, it's just like B. It doesn't really play that much of a role. But now we square that. Now comes D squared. Have D squared, and the graph looks like this parabola. Not to scale, but you get the point. you see how, so normally, if it was just 1D, then it just wouldn't change much. The more you add, same amount of difference. But you see, this slope is like woo, goes like whoosh, plays a much bigger role than if it was just regular D without the square. So yeah, D plays an important role, much like H, maybe just not as important, but still quite a difference, right? Does that make sense? Does all this make sense? I know that's a lot to ask, but is this making sense so far?
You're talking about like, okay, we start out with the regular 2x4. That's easy, but then like any other structural members, most likely made up of just rectangles.
Mhm.
So just break the rectangle. The sum of the rectangles will get you the inertia of the more complicated structural member.
Right.
Yeah. I guess I'm trying to like read back what you're telling me, right? That's what I'm trying to say.
Mhm.
But yeah.
So we've gone over a bunch of variables. We've gone over a few formulas. Do I have any other formulas to go over? Okay, I do have one. Deflection. There's a formula for deflection. Wait. Deflection. Ah, wait. Where did I get this formula? Oh, okay. Found it. Right, so we have a formula for deflection, and that's just going to be P L over A E. Not epsilon, E. P, load times the length of the rig. Load times the length of the beam divided by a area times the elastic modulus of the material. So this is load. That's going to be like in kips or something. This is going to be a length that's going to be like inches or something. Area inches squared. And then elastic modulus, KSI, so kips.
So wait. I thought P was the axial force.
Axial force. Did I say something different?
Okay, I don't really remember now, but yeah, that's I'm just double checking. P is
Okay.
axial force times length, right?
Right. So this is just the load, or well, you can think of it as the load.
Oh, okay, the load. I was getting confused. My bad. So don't call it axial force.
I guess, yeah. Just think of it as the load.
Okay.
Huh.
Just wanted to make sure I was understanding
Yeah.
it correctly between the word load and like seeing P labeled axial stress above.
Okay.
I got you.
Yeah, that's now that you brought that up, that's a bit weird. But still, P is gonna be a force, kips, or pounds, Right, so we have the area, so this elastic modulus is kips per inch squared, right? So we can just solve this real quick. Inches squared, these cancel out, kips, these cancel out, so you're just left with inches. And we all know deflection is in terms of inches. Cool. But let's get some more derivations. Right? Oh gosh, that's a little far. Move this boy up to hither. That is not right. Okay, I'm just gonna delete that. I'm gonna rewrite that. So again, a lot of formulas here. I think this one is the least intuitive. So if you don't remember this one, I would not blame you at all. I think this one is the least intuitive of the formulas. But we can actually derive that in a sense. Let's see. How would I do that? Let's see. All right. Okay. So in order to derive that, we need to derive. We have a different thing to derive. We have another formula involving section modulus. So moment divided by section modulus is equal to deflection, I think. Look, give me a hot minute. Section.
I think it's for stress.
For stress, yeah. This. Stress. Moments. Stress. Okay, I'm gonna go over this formula later. If I figure it out. Right. So. Okay. E. Okay. So, cool. Okay. So, there's another formula for E, actually. I forgot to go over this. So E, deflection over length. Easy stuff. That's an inch over an inch, right? There's also a different way of calculating E. It's from stress divided by the elastic modulus. Let's see. Yeah. Okay. So this is just another formula for deriving E, the amount of stress. Yeah, and this makes sense. You know, stress, elastic modulus. So elastic modulus is the limit amount of stress in a material, right? And then let's just say we have our steel beams. I forget what it was, but like 8,500 kips per square inch KSI. And you apply a load on it or a force on it, and you get a stress of like 50 KSI. It would get like it's like it would create the same amount of proportionality in a sense. So elasticity, strain through deflection and length, sort of, it's like a natural. It's just an observation of how much the beam deflects, depending on the length of the beam as well. But this formula, with the stress and elastic modulus, it's more of an intuitive understanding of what the actual material is made out of. So you need to know what material it is, so you can determine the strain. So these are just two different ways of getting the exact same formula. And we can actually use this right here to derive this formula up here that we got. Remember I said this is the least intuitive? Well, it is actually a good way of it's a good way of simplifying an equation if you don't have all the materials you need or all the variables you need. So what do? We just set these equal to each other, right? Because they're the same thing, so you can just set them equal to each other. Delta over L is equal to sigma over E. Does this make sense? Does this make sense? Just basic algebra. Because they equal the same thing, we're going to set them equal to each other. You don't really have to pay attention to this. This is just small intuitive understanding how this works. We did not go over this in class at all. But
no, but it could be helpful. Like you're saying, like if variables are missing, this is how you can fill them out.
Yeah. So remember, we want to solve for deflection, right? We want to get to this formula right here. So we're going to multiply L to the other side. So this becomes delta equals L sigma over E. You see, we're almost there. We have L and we have E. We just don't have P and A. Well, hold up. P and A is is determined by stress, or stress is determined by P and A. So we could just replace stress with P and A. So deflection equals L times, we're just going to replace stress with P over A. Divide that by E. And then because the fraction divided by a fraction, we can just simplify that to deflection equals L P over E A. Sports is in the game. EA. So, and you see, we just derived that function.
By the way, I love you for that. That was the best one of the whole night, right there.
Thanks. Yeah. So yeah, that's just using these two formulas, which use the same solve for the exact same thing, setting them equal to each other, replacing sigma with P over A, and we just get that formula. Fun stuff. Fun stuff. Cool. If that helps someone, cool. If that didn't, just forget that. Not essential or not necessary to know at all, but something cool to think about. All right. Now what? Let's go to safety, or whatever it's called. Sustainability? No. Safety. Probably safety. So, right. We have moment divided by section modulus. Moment is kip inches. Kips times inches, so force times a length. And section modulus would be inches squared. So divide that out, that would become kips per inch. This is strength. Or is it? Wait, crap. No. Inches cubed. Okay. Jeez. All right. So kips times inches. So this would become kips per inch cubed. Kips per square inch. So that's just a stress, right? Good stuff. We can actually use this formula to derive certain things. So let's see. Equals sigma. So remember, this is stress. We can actually use this to solve. We can actually replace stress with yield strength, F sub y. Now, this is just a different term for, this is just, this is stress. This is KSI in terms of KSI. But it's just like a sort of limit, kind of like E. This is a sort of limit that we want to reach. So it's kind of like E. So E is the limit. But this is the serviceable limit in a sense. So this is the limit to failure. This is the limit to usability. So it's Fy. That's just Fy. That is yield strength, and this is going to be determined by. This is probably going to be given to you. I like to use in a problem to solve. You know, the maximum yield strength. You know, like that's cool and all, but you know, we don't want that to be the absolute limit of serviceability, right? Let's say you don't want a beam to handle more stress than like 5,000 KSI. That's a lot of KSI. 500 KSI, right? You don't want to set the limit at 500 KSI because you know, due to normal distribution, it's probably going to go over. So we just want to reduce that. This is for serviceability. We're just going to multiply that by 0.66. Just so we can just so we can artificially lower the limit, or yeah, lower the limit, right? So this just takes into consideration like this 0.66 just takes into consideration like fluctuations in load that would result in higher or lower stress. This just takes that into consideration. Okay. I think that's all the stuff. We do have a little bit more to go over. I just want to go over the question that Klebus went over in class really quickly. But any questions on anything that's on my screen right now? Any questions?
So would you categorize FY like as one of the things we're listing, like deflection, stress?
Yeah, I would.
Or not? It's something different.
I would. Yeah, list this as like one of these.
Okay, that's how I have it listed.
Yeah, like I would group it with like P, A, L, because they're not really they're not like set terms. These are just yield strength is more of a placeholder. Does that kind of make sense? I don't know. But it's not as important as deflection, stress, elastic modulus, strain, inertia, section modulus. I think these are the most important ones. And then after that, it would be yield strength, force, length, area, right?
Gotcha.
Okay. There is one more variable, just one more small variable. It's K. This stands for stiffness. And I believe this is referring to inertia. So K is just a placeholder term for inertia. So K is just inertia, which is inches to the fourth. This was like gone over like very briefly in class, so I'm not entirely sure on this one. But that's just another term that he went over, or that was mentioned at least. Fun stuff. Any other questions? All right. Welp. We're gonna move on. This is the last thing I'm gonna go over for tonight. Just gonna do a quick review of the final problem that Klebus did in class. So I'm just gonna keep all these formulas. Resize that to 50. Gosh. Size that to 50. Okay, beautiful. All right. So I'm just gonna keep that. Keep all that over there. And we're just gonna mark that off as formulas to use. This is very messy, so I will circle what we will be using. All right, so this is just going to be literally what we went over in class. So for the last bit of Wednesday's class, the most previous Wednesday. Right, so we have a steel beam, length of 30 feet. Fun stuff. W. What is W? Oh, if you look at your very handy dandy shear and moment diagrams, you will see that W is actually the variable they use for load, or in this case, a linear load. So yeah. So we're going to be using, let me just make sure it's going to be inside the webcam. We're going to be using this boy. So you can see how we have L, length of the beam, and then W for the linear load. Just keep that in mind. It's just what we're going to be doing. W is 1.5 KLF, kips per linear foot. For every foot on this beam, there's going to be 1.5 kips of force on that. Fun stuff. E. This is steel. Steel. E is 29,000 KSI. Right? It's steel, it's metal. It's probably a wide flange beam, so a lot of resistance to stress. And let's see. And then our yield strength. So this is what we want to reach, I think. Yeah, this is going to be our serviceability limit. It's going to be 50 KSI. So we don't want to go over this 50 KSI, right? So like, I think one way you can think about it is, this is our beam, right? 30 feet. 30 feet, we have a KLF of 1.5 KLF. Fun stuff. So like people are gonna be walking all over this, right? We don't want this to deflect that much. Like it can deflect a lot, you know, it could deflect like a foot, but no one wants it to deflect a foot. So it can definitely hold more than 50 KSI. It can hold 29,000 KSI. But let's stick with 50 KSI so it doesn't move as much. Staying way away from that failure load. All right, so what do we want to do? We just want to find, what do we want to find? We just want to find inertia. Wait. Inertia, yeah. And deflection, all right? So we're just gonna figure out some values of this, all right? So what's the first value we can figure out? Well, if you look at this super handy dandy chart that the Klebus gave us, we can solve for shear force, maximum moment, and maximum deflection. What do you say we solve for maximum deflection, or maximum moment first? Look, taking directly from the chart, and remember this is a simply supported beam, uniform line load, right? Same exact picture. Taking directly from the chart, this is going to be moment equals W L squared over 8. Fun stuff. I will denote this in blue, saying this is from the chart. And then I will denote a red dot for one of these equations. So equation, right? So fun stuff. We just got all that. Plug that in. Blamio, and you will get M equals. Where's my calculator? There it is. M equals, let's see, 1.5 times, but 30 times 30 divided by 8. That is beautiful. 168.75 moment kip feet. Cool. Now what? Well, what can we use moment for? Let's look over here. We can use moment for serviceability. See, moment over section modulus equals what was this called? Yield strength. We don't know. It's a section modulus. So you know what? Let's solve for section modulus. Right. So we'll just take this formula. Actually, we won't be taking that formula. No. Have to make it serviceable. We're going to take this formula. So technically, we don't want to use this formula for now, or ever, I think.
Wait, there's two different formulas? Hold up.
So this formula. So okay, yes, there are two different formulas, but there's a reason for that. Right. So this formula, this is just a direct conversion, right? This is a direct conversion. In a perfect world, we would use this formula. You know, moment divided by section modulus equals the yield strength. So you have a yield strength of 50 ksi, and you already have a moment. You would figure out what sort of material in a perfect world, right? But we're not in a perfect world. The yield strength determines the limit of what we want the stress to be. But we all know that stress will change, right? It's gonna fluctuate up and down. There could be more people coming in. There's gonna be more furniture, less furniture. You know, we got to take into consideration this sort of indeterminality of what of this building, of this diagram, right? So in order to take that into consideration, we're just going to add a small modifier, 0.66, right? So it's just gonna reduce like the severity by a third, you know? So like making the limit smaller will account for the fluctuations. Does that make sense?
Yeah, like you have to add this factor in for a real world situation. Okay.
Right.
I got you.
So.
Okay, my bad, because I was gonna use the first equation, then I saw the second one. I was like, oh, what? But now I get it.
So let's draw a normal distribution right here. So let's say this is the load of. This is just the daily load, or daily stress of the building. Let's say we use the first formula, right? Right in the middle. In a perfect world, it would always be at this point, you know, 50 ksi. But we're not in a perfect world. It will fluctuate this way. It will fluctuate this way. It'll fluctuate all the way over to 100 ksi. And it will very easily fluctuate to 100 ksi. Like half of it is below it, but half of it is over it. It could very easily go over this yield strength, right? So what if we just, you know, change that? Not make this 50 ksi. Let's multiply that by 66. Make that 33 ksi. Now we're getting somewhere. Where's our yield strength? Where's our maximum yield strength now? It's all the way over here, or somewhere, 50 ksi. Right? So now you see a majority of the time it's going to be below the yield strength. It might still go over a bit, but it's less likely, you know? So we wanna lower the limit. So it just in the matter that in the situation that we do go over, in the occasion that we do go over, it'll take more to reach that upper limit of 50 ksi. Does that make sense? Or no? Does so? All right.
Yeah.
You statistics nerds out there, this is probably an interesting analogy. But anyway, we don't want to do this. We want to be safe, so we're going to multiply this by 0.66. All right. So Just going to take that moment and that yield strength. We're going to solve for section modulus. Section modulus equals to moment divided by 0.66 yield times the yield strength. That would equal 168. I'm just going to do 169 because it's very fast. 169 times 0.66 times 50 KSI. 169, that's kip feet. Oh, wait. Oh, crap. That's not right. Now, the problem is this is... Clevis messed up? Hold up. You'll see the problem, right? Because we have kips per square inch and we have kip feet. So, hold on. Let me see if this actually works. Probably it shouldn't.
No. Yeah, he realized that something became like 0.2.
Yeah, kip feet. Yeah, okay. Right. So we have to convert this kip feet into kip inches. How do we do that?
Times 12 inches, right?
Times 12 inches. So you can multiply it by
169 times 12.
12 inches over 1 foot. So now, 12 inches over 1 foot, that equals 1, so you can add this in. So this foot cancels out with that, so you just multiply all of that by 12, and then you should get the correct number there. There we go.
2028, yeah?
Wait. 169 times 12 divided by 0.66 divided by 50.
Oh, the whole answer. Well, yeah, 61.5.
Equals 61.5 inches cubed. Yep.
All right, cool.
Yeah. So now I got the section modulus. Fun stuff. Let's solve for deflection. All right. So, this was something we went over in class that you might not have gotten. So when you think about a beam, right? There's always going to be some sort of deflection in there, right? But you don't want the deflection to be so big that it's like going to be noticeable. All right. So Clevis actually gave us some limits to what deflection should be. So total deflection of everything, total deflection. So you have the beam, you have the loads, you have just everything on that. Total deflection should be no more than the length divided by 240. So for the live load deflection, you have the live load, which contains people, furniture, office equipment, tables, everything that wasn't part of that, everything that's non-structural deflection. Should be L divided by 360. So, and there's one more. So masonry support, deflection for the maximum deflection for masonry support should be no bigger than L divided by 600. Well, there's some variation between it, but between L over 600 and L divided by 720. So what does this all mean, right? For masonry support, you cannot have that much deflection, right? Like you have 600 inches of masonry. It cannot go more than 1 inch of deflection. It's important for that to be stable. Live load, you have 360 inches. It cannot bend more than 1 inch. Or it cannot deflect more than 1 inch. For everything else, you add on the structure and everything, it cannot bend. It can for something that's 240 inches long, it cannot bend more than 1 inch, right? So, you know, this is just some guidelines to set how much your floor should deflect, right? So we're just gonna be most conservative. We're gonna use this total deflection right here. L divided by 240. I will keep that actually. I'll take that. I will resize by 50. Bam. Keep that in the corner. So we're gonna use total deflection, right? Let's see. Back to here. Deflection should be L over 240 inches. Oh, no. Just 240. So now what is our thing? How long is our beam? L, that's 30 feet, which is 360 inches over 240. So our total deflection should be, our maximum deflection should be 1.5 inches, right? Cool. So now we finally get to the last bit. We're gonna calculate for inertia. Now, how do we calculate inertia? We can use, you might be thinking, we can use, where is it? This one. Section modulus equals inertia over half the height. Well, we don't know the height, you know? We don't have that, you know, so we're not gonna use that formula. I said I would be labeling things. So equation. So this one is an equation. It's from here. This one is an equation. That's this one. Just gonna circle the equations that we've used. Moment. This came from the chart, from the shear moment diagram chart. Section modulus. This came from here. Serviceability. This deflection came from here. And now we're going to use one more formula. We're almost there. We're going to use maximum deflection right here. This formula on the shear right there. Problemio. Cool stuff. So, right. So I'll just write this out real quick. Deflection is equal to 5 times W L to the 4th divided by 384 times E times I. And we're going to be solving for I. How did we come up with this formula? Calculus. Even I don't know, but it probably doesn't even matter. Like as long as you have this formula, you'll be fine. So this is very handy. So you don't have to calculate everything by hand. You know, take the easy way. And if you want to learn it, then cool. Go on Wikipedia. Very confusing on there. I think I tried to learn why this is on the Wikipeds, but I just couldn't. Anyway, so we are solving for I. So we're just gonna switch deflection and I inertia. So I is equal to 5 times WL to the 4th over 384 times E times deflection. Fun stuff. Cool. So for the big finale, I is equal to 5 times W, which is 1.5 KLF. In foot, we want that in inches. So 1.5 times 12 is 18. So it's 18 KL. Hold on. I just want to double check real quick, just so I will lead you guys in the right direction. So just give me a moment while I just type this out. Fourth. Okay, and then 184 times E. That's or deflection. That's this doesn't look right. That's not right. Give me a moment. Oh, frig. That divided by. I'm multiplying by 12 too much. Let's see. 5 times. This is weird. Damn, I wish I had memory. I'm just gonna scroll up in my calculator to see what I did. Where did I get? Oh, I'm dumb. Okay, all right, cool. Okay, I feel so dumb. All right. Let me just 5 times 1.5. Okay. All right, this should work. Times. All right. Okay. Cool. Okay. So for the big finale, sorry about the delay. For the big finale, we are gonna solve for inertia of this beam, this steel beam. Right. So we have 5 times W. Now that's kips per linear foot. So we. Oh. Wait. That's weird. Wait. Right. Okay. Kips per linear foot. So we're gonna. Right. Okay. Sorry. Okay. Kips per linear foot. So we're gonna divide that by 12. 5 times 1/12. Or I'm just gonna divide that by 12. Okay. This makes sense. 1.5 divided by 12. Why do we divide by 12 instead of multiply by 12? So if you think about it intuitively, right? You have, let's say this is an entire foot. Let's say you have 1.5 kips. You divide that up into 12 sections. Each section would get 1/12 of 1.5 kips. So you just divide that by 12 to get kips per linear inch, right? Also kips per foot. You can just multiply that by 1 foot over 12 inches. And you just get kips per linear inch. Anyway. I ramble. Anyway, back to this. Big finale times 30 feet. It's in feet. We have to multiply that by inches times 12, right? That would become inches to the 4th divided by 384 times what is our E? 29,000 KSI. It's in terms of kips and inches, which is beautiful. And our maximum deflection, which is 1.5 inches, and we get 628.448 inches to the 4th. Why is that important? Well, now we can look at all the different types of beams and look for a beam as this or greater than this. So I is equal to that. So you can look for this problem, you will have to find a beam that has an inertia of 628.448 inches to the fourth or more. You know, you can have a beam with more inertia to handle more load. But we already took that into consideration. This is the maximum load. This is the inertia we need. We'll be fine. And you know, Klebus told us about the steel construction manual with literally it's a boy that's like this thick with a whole bunch of beams. You just flip through that, look for something that look for an I-beam, wide flange beam that has this inertia value or greater, and that's why we did all this, so we can find a beam that would fit this situation. Did that make sense? Did that not make sense? Oh, Allie's here. Hello, Allie. Did that make sense to everyone? Hopefully. Did that not make sense to anyone?
Yeah, that made sense. I get this is like the same problem that Clevis had done.
All right. Well, that's all I have. Questions about anything? Any questions? No? Well, that
How's
concludes.
life?
Oh,
That's my question.
that's your question. Well, it is complicated, I will say.
That is very true.
Very complicated. Yeah, I'll leave it at that. Questions? More questions?
We're gonna get on the craft, or we're gonna kill the Ender Dragon tomorrow.
Let's get on there.
Dude, I could go for a nap right now. I'm not
You
gonna.
could go for a nap. All right. Well, probably tell the server. We'll probably tell Felipe. We probably have to do it tomorrow.
But I can do it right now, though. I have a coffee.
Any more questions?
Same. I'm dead tired, bro. I need to like.
All right, we'll probably just do it tomorrow then. Sorry, Felipe.
Yeah. Let's let him know. And plus, the server was acting weird anyways. Jason just joined on that good stuff. But Edison, once again, thank you for.
Of course.
So I will catch y'all
All right.
somewhere else.
I'll stop recording.
I don't know. You guys want to hop on the Discord, maybe?